Okay. That's what I forgot. That sound there. Okay, now we are ready to get started. So we are still talking about business applications. It's our third day of this. We'll go through the one more example of what we did the last time with the more complicated total cost curve, the cubic one, and then we will have two more examples where we take our more complicated total cost curve and combine that with a total revenue and sort of this kind of profit curve. And we'll try to, sorry, that's backward. This kind of profit curve, and we'll try to see where the best point could be on that curve based on our more complicated functions. So that's the plan. I do have some extra slides put in about some extra derivative rules, which I didn't have time for in the other class. So maybe we'll have time for that. I don't know. We'll see. But that's the plan. So one of these cubic again, and like an x cubed kind of thing, and then combining it like that, and then one more like that. But we're going to do a bunch of review stuff before that because it's been a long weekend and probably some of you forgot. So that's the plan. Just quickly, final exam, I'll announce this again. So we're on December 13th. It's that Monday evening. Hybrid, if you're wanting to come on campus and do it here, I have these rooms booked. Just fill out that form on our classroom page because I need to know how many people are coming and plan seating and print off exams and all that. Or if you're going to come online, just it's the exact same as we did the midterm scanning and selfies and all of that. So if selfies are annoying for you, then come in person. Your choice. We do have another, or so I'll mention this. The actual exam time will be 2 hours. Midterm was 1.5 hours, so there'll be a bit more time for you to work. And since people need to come, if you're coming in person, you have to come a bit early to get everything set up. If you're online, it takes more time to do scanning and selfies afterwards. So we do have one more makeup class that's officially scheduled. For the other section, I know when it is. For you guys, it's in, maybe it's the Tuesday of that week or something. Anyways, the exam will count as that makeup class. So the makeup class that's on the schedule for week 16 for us, just come to the exam instead. If you come to the exam, we will mark you as present for that day. So the exam is the only meeting, the only thing that's happening with our class in the final week of the makeup week. Review plan today, sorry, not today. Next class, we will do just, I mentioned this last time, just kind of concepts and formulas and the basic method for solving various problems, but we won't actually solve practice problems. That will be the 2 days next week. So day 1 next week will be pre-midterm material, and day 2 next week will be post-midterm material. So lots of different planning days coming up, or sorry, review days coming up. So hopefully we'll all be well prepared. Any questions about exam related things? We're okay? Good. All right. So from last time, let's see if we remember this stuff. I told you that there are many ways that we can write out derivatives. Do you remember them? First, how many ways are there? 4 for each. Okay. First derivative, what can we do? All right, y prime is one of them. Okay, f prime of x. Okay, dy over dx. Derivative of y with respect to x. x of f of x, like this. It's not a fraction, but again, if you kind of imagine it as a fraction, this thing on the top, we can just kind of write it out on the side. That would be the same thing, but still it's not, that's logic happening, but even so, it's not actually a fraction. Okay, so that's first derivatives. What about second derivatives? Okay, so y, and we read this as double prime. Y double prime, or, okay, f double prime of x, or d squared y over dx squared. That second one there. Again, this is not actually exponents. It just looks like them. It just means do the derivative process twice. And our final one, squared over dx squared of f of x. In my other class, some people were thinking that we have to put a little prime there or a double prime there, but we don't. This is the part that says that it's a derivative. So we don't put those there. All right, lots of ways to write these things. We need to be familiar with all of them. Right, next. Marginal revenue is mathematically the same as what other thing? Okay, derivative of total revenue. Let's practice our notation. We can write it like this way. D, and then it's a Q on the bottom because that's the main variable that we have in those equations, not X. So it's the derivative of total revenue, and marginal costs, then exact same thing, except derivative of total cost. As I explained, not last time, 2 classes ago, this concept of marginal, like what happens, what's the change in some value if another value goes up or down by 1, that's the exact same concept as what slope is, and derivatives tell us slope, so marginal cost is the derivative of the original cost equation. Marginal revenues, derivative of total revenue. Okay, so very important relationships to understand. Okay. All right. All right, we're going to spend a little bit of time on this one. See if we remember all the parts. First part, sorry, I'll just give you a second. You can read this, and then we'll start talking about it. Okay, so we've been using these derivatives to find key points of these functions. Before we touch the derivatives, what can we look at to just get a basic idea of what it could look like for polynomial functions? This was from 3 weeks ago when we talked about visually identifying these functions. Okay, so the ends and going in what direction? What do we look at to figure that out? Okay, so the leading term here, Ex1. So some big long polynomial, the coefficient and the exponent of the leading term. That's what we care about. All right, so if I have the leading term that's like this, ax to the exponent n, What is the largest number of zeros that we could have? Let's say we have an exponent of 5. What's the zeros, the x-intercepts of the function? The minimum number of zeros is 0, or if it's an odd, then it'd be 1. Like we could have an x squared that's like this and it never touches. What's the maximum number of zeros? Okay, that exponent. So n, or in this case, if we're saying 5, then it'd be 5. So that's the maximum number of times that the function can cross the x-axis. What about turning points? What's the maximum number? Okay, n minus 1 turning points at most, and how many inflection points? Minus 2. We're going to the second derivative. So this should kind of make sense, because if we had an exponent of 5, and then if we did a derivative, then the largest exponent would be a 4. If we did a derivative again, largest exponent is 3, and dot. Eventually, we just get to an x with no exponent. That would be a straight line that can only cross one time. So that kind of pattern is what we're thinking about. So that gives us an idea of how many possible turning points, and then also the leading coefficient here. What does this tell us? The sign of this a term? If it's positive, then what will the function do? Okay, right side will be going up, and if it's negative, the right side is going down. And what else can we get from the exponent? Okay, so if we're going in the same direction as whatever the other thing was, then that means we have an even number, not necessarily up, but the same direction as the other one. And if it's going in the opposite direction, we have an odd numbered exponent. So we can get a lot of information just with a quick look at the leading term and know, okay, probably or at most this many turning points. If my exponent's a 4, but I have like 6 turning points, okay, something's gone wrong there. So just a basic sense of what the function could look like will be very useful and can help you catch mistakes. Okay, so now let's talk about the other part of this. How do we find zeros of a function? We've been doing it a bunch of times. What's our process? We don't necessarily need to factor. Okay, so we just set our function equal to 0 and then solve for x. So when y is equal to 0, x is whatever. And those numbers, those are your zeros. How do we find turning points? First derivative equal to 0, and then solve for x. Okay, and then what about inflection points? Second derivative equal to 0 and solve for x. Okay, that will give us inflection points. That will give us the locations of these inflection points and turning points. For turning points, how do we figure out the type of the turning point? One more time. Okay, so we take these x values from our first derivative and we put those into the second derivative. And we figure out, well, is it greater than 0 or is it less than 0? And that gives us, it will tell us what type we have. Inflection points. Do we have a way to find the type of an inflection point? Do we have a way to find the type of an inflection point? Okay, we have not talked about this, but just like the turning points have positive to negative or negative to positive, the inflection points can also be like curving down to curving up, or they could be curving up to curving down. And to find out what type, we could do a third derivative test to do that, but we don't really care. Honestly, I've never seen a textbook that teaches how to do that because it's just not really useful information. If we want to know that, we can just kind of look at the turning points and say, oh, this is a minimum, that's a maximum. So, okay, this is what it's doing. So theoretically, it works, but we don't really care about that. So types for turning points is the thing that is most interesting to us. Okay. That was that review. This stuff we're gonna do with our examples today. So let's we'll answer these questions on the right here with today's example. So I'll just kind of skip over that part for sake of time. Okay, so hopefully these processes are getting somewhat familiar for us. We had these ones last time. We had this demand function that was in terms of Q, but then we rearranged this to be in terms of P. And then we use that so that we got a total revenue equation that was in terms of Q. So sometimes we might have to rearrange the demand function like that. That's what we had in the last class. And then we talked about these profits. And we did this example with a minimum marginal cost. And where did the minimum marginal cost happen? Or how did we find that point, rather? You don't need to remember the number, but how did we figure that out? One more time. Okay, so derivative of total cost is marginal cost. How did we find the minimum marginal cost? Turning point of minimum costs, or in terms of total cost? What's happening right there on that function? What kind of point is that? Okay, so this is the inflection point. Minimum marginal cost is happening at the inflection point. We have this curving down, becoming more efficient, and then curving up, becoming less efficient. So the second derivative, inflection points, and that's how we figured it out. Okay, so I have another example, the exact same style as this, just with different numbers. So go ahead, try to find the minimum marginal cost for this scenario. Does anyone have an answer? Or just a Q value? 30. For marginal cost, you say 3,520. All right, we got some answers in the chat. 15, 30. So let's see what we get. Or let me write that down here, maybe 15. Okay, so first thing we will do is what? All right, so marginal cost. We need our first derivative of our total cost here, which is Q squared minus 60Q plus 2,800. All right, and then what? Second derivative. So just we'll do this again. So marginal cost prime, which is the same as total cost double prime, is 2Q minus 60. And then, all right, we set this equal to 0. So I'm just gonna write this a little shorter here. 2Q minus 60 equals 0. So Q equals 30. So that's actually pretty quick. By the time we do a second derivative, this function gets not very complicated. It's just no exponent even. We can solve that pretty easily. So there's the Q, 30. That's where our minimum marginal is happening. And now what do we need to do? Okay, so we want the actual dollar value of minimum marginal cost, not total cost. So we're going to take this and we'll put it back into the marginal cost equation. So we had 3 of them: total cost, marginal cost, derivative of marginal cost. Make sure you're substituting it back into the correct thing for what you're looking for. So marginal cost when Q is equal to 30 will be Q squared plus 60 times 30. Yes, you're right. Thank you. Minus and plus 800. So 900 minus 1,800 plus 2,800. 1,900. So there we go. Not too hard to solve. Everyone's finished writing? Okay. So there's our inflection point for this total cost curve. This is our most efficient point. And so item number 30 has the lowest cost, the lowest per item cost, the individual cost. So if we made 31 things, item number 31, the cost for that item would be greater than this 1,900. Item number 29 would be also greater than that thing. It would have a higher cost. This is our minimum per item cost, which also gives us our minimum average cost for all the things that we're producing. All right, let's go on to our next example, getting a little more complicated here. The other classes told me that in microeconomics, you guys have been talking about this concept, perfectly competitive versus non-perfectly competitive. Yeah, okay. Can someone just tell me what this is, or can you give me an example of a product or market that is perfectly competitive? Water?
Coffee.
Most of the time. Did you say coffee?
Yes.
I don't know about coffee. You can buy like really cheap coffee at McDonald's or something, or pay $10 at Starbucks. Like premium coffee is a thing.
Fruits.
Apples, fruits, yeah. In some Korean stores, you go to E-Mart, you can buy like fancy apples, but let's say something more boring, like onions or garlic. I've never seen like premium onions. They're just all the same. You don't care what kind. If they're not rotten, then you buy them. So there's just kind of a standard price. So price is just perfectly flat, and that happens because if for some reason you try to charge more than everyone else does, you're charging more than everyone else, nobody wants to buy your product. It's the exact same product for more money. No one buys your thing, you go out of business. If you find some way to charge less money, then you are now not earning a profit and you go out of business, or you have found some clever way to reduce your costs, and everyone else now needs to copy you and have the same price as you. Otherwise, they go out of business. Or like gas for your car or something. You don't say like, oh, this is your favorite gas station or something. Oh, my car likes this gas better. It's just whatever one has the cheapest one. So that's a perfectly competitive market. So our total revenue in this case would actually be just a perfectly straight line. Doesn't usually happen, but can happen. All right, anyways, that's a little microeconomics review. So we need total revenue, total cost, and profit equations to begin with. How will we make a total revenue equation? How do we define total revenue?
P multiplied by Q.
Okay, let's do the total revenue first. So it's P times Q, and if P is 121, what's our equation? The total revenue first. So it's just 121 Q. That's it. So very simple. If we have this simple demand function here, our total cost, as we heard, it just variable cost plus fixed cost, just add them together. So 1/2 Q cubed minus 15Q squared plus 175 Q plus 500. And then for profits, we just take our total revenue, 121 Q, and subtract our total cost. So while I'm writing this out, you can try to simplify this and tell me what our next line will be. Okay, so I want to order this in terms of the largest exponents first, just to keep this organized. So what are my terms going to be here? Biggest exponent first.
396Q.
Okay, so the negative 1/2 Q cubed, that's first, plus 15Q squared minus 54Q minus 500. Okay, so let's notice a few things about this. So leading term here, largest exponent, it's negative. So we're going to be going down on the right side here. Also, the constant is a negative number, so we're starting down here. If we have sold nothing, then we have earned no money. We have just spent fixed costs, so we're in the hole. We're in the negative, and we have to actually do some work and sell some things before we can go positive. So the shape is probably going to look something like this. We'll kind of have some small area where it goes positive. And so most of our terms are negative. The leading term is negative. The constant at the end is negative. But in the middle, we might have one or two positive terms. So that's just a basic thing we can check. I see lots and lots of mistakes with people forgetting about this bracket here, and they don't apply this negative to all of the parts, and like all of their terms are negative or something. So lots of possible mistakes. So leading term for a profit equation like this, probably negative. And the final term, the constant term, also should be negative. If we get those signs wrong, it completely changes what our answer will be. Okay, so there's profits. And that's the first part. So now we want to find the Q value where profit is maximized. How can we do that? Find the value for Q that will maximize profit. Substitute what? B, right here. We want to find the Q value that will maximize our profit. First derivative. It's the same as before. Maximums and minimums are just turning points. Those come from our first derivative. So first derivative of profit. Profit prime will be -3/2q squared plus 30q minus 54. Okay, we have a quadratic and we want to solve for q when this thing is equal to 0, 3/2 squared plus 30q minus 54. All right, so we can factor out the -3/2. All of these things will divide cleanly by 3. So that's the first step, -3/2. What will my other terms be? If we take out this factor of -3/2. Basically, we are dividing by -1.5 or multiplying by -2/3. Multiplying by -2/3. We have this factor 3/2, so we do the opposite. Okay, so what will our next term be?
Minus 20q.
Okay, -20q and
-36.
negative or positive?
Positive.
Positive 36. So negative term we're factoring out. So the signs on each of these things are flipping and multiplying by 2/3. So 30 times 2 is 60, divided by 3 is 20. Same thing for the 54 there. All right, so let's try to be lazy first. Let's see if we can do our sum product method. If not, we could do quadratic formula or completing the square or those other methods. So can we see two numbers that add to -20 but multiply to +36? Add to -20, multiply to +36.
-2 and -18.
-2, -18. -2 minus 18, -20. That works. 2 times 18, 36, and they'll turn out positive. Okay, that's going to work. So we have here q minus 2 and q minus 18. So based on this, our solutions for q here, q equals 2 and q equals 18. We have those 2 points. All right. So the question is asking us about the maximums and the minimums. We really care about the maximum. Maximum profit would be nice. What can we do to find that? Okay, so we have 2 points. Which one's the minimum? Which one's the maximum? We have a negative q cubed. So we probably have this shape. We probably have the first one as the minimum, second one as the maximum, but let's confirm. We don't know that for sure. Second derivative test here then. So profit double prime is, what is our second derivative? -3q plus 30. Okay, and we'll take our two q values and substitute those in here. So our second derivative of profit when q is equal to 2, that will be this -3. We don't even need to write that in. -3 times 2 plus 30. Okay, that's going to be a positive number. So when q is equal to 2, second derivative is going to be positive. And when this thing is 18, when q is equal to 18, our second derivative will be less than 0, negative. It'll be -24. So for each of these then, which one is our minimum? Which one is our maximum? Okay, 2 is the minimum, 18 is the maximum. Just to remind us how that works. If the second derivative is positive, that means the slopes are becoming more positive. They're getting closer to positive infinity. If we're curving up like this and we have a flat slope, that can only happen at a point like this. So that's a minimum. And opposite for the other case, if our second derivative is negative, slopes are curving downward. Flat points can only mean that we have a maximum point like this. All right, so we have at this point now answered the question. We've confirmed when q is equal to 18, we have a maximum profit, and when q is equal to 2, well, do we? We'll come back and answer that in a moment. But let's see if we can do one more step here. What is the actual maximum profit? How can we find that? Okay, so we take our q value, this is the location of the maximum, into which equation? profit equation, just the original profit equation here. We can figure out the location. We got some time. I have to erase something, so you guys can try to calculate that while I make some space here. So try to tell me what the actual maximum profit will be. Happens when Q is equal to 18. $472. So max profit, you're saying, is happening when we calculate our profit equation for when Q is equal to 18, and the substitute Q into this whole thing, and ... 472. I won't go through all the calculations of that here. My notes also say 472. So I'm confident that's the right number. And that's how we can figure out our actual maximum profit here. Any questions about the math part of this example? I do have the graph to show you, but I need to erase some stuff to show that. So any questions about what work we've done here so far? No? We're okay. All right. Then yeah. Do this. Oh, there we go. Okay. All right. Here is our graph. We can notice that our maximum for our profit is happening here, where Q is equal to 18. Same thing the graph is showing us. We have a break-even point here and here. We didn't calculate them, but we can see approximately where they would be. And so this is all color-coded. The blue one is total revenue, red one is total cost, purple one is profit. So where the blue one and the red one meets, that's where total cost, total revenue are equal. That's also the break-even point on our profit one. And this intersection point here is the same as our other break-even point for profit. So it looks like we have a maximum profit point here where Q is equal to 18. When we did our earlier stuff talking about polynomial functions, this kind of maximum point, is this a local maximum or a global maximum? Okay, the local maximum. So why did we say this, like the function goes way up to like positive infinity here. So why are we saying this is the maximum profit? Right, so over here, Q is negative. Like we can't, your factory can't make negative number of cars or negative number of phones. So if we wanted to be very careful, we would test our 0 points and just make sure that the left side isn't going really high and positive. But for a profit equation, that's basically going to be impossible. And we can also see here the constant is negative. So we're starting at a loss, and hopefully we do get to a profit at some point. What about minimum? We have a minimum point happening where Q is equal to 2 happening here. So this is also a local minimum. What is the lowest possible profit? Where does that happen? And Q equals 2, is that the minimum possible profit? Is that the lowest possible profit? Yes or no? When Q equals 2, lowest possible profit? No, the right side goes way, way down here. So lowest possible profit is like negative infinity, like, or because our total cost is now raising really high, really steeply at that point. So your profits are going like way, way down, very negative. So in this case, the local minimum, we don't really care too much about it because we have much lower values down here on the right side. But this local maximum is our best point because on the left, we can't have a negative Q value. That doesn't make sense. Okay, so the algebra stuff, kind of the similar derivative processes, but also good to be able to just kind of look at the graph and kind of have an understanding of how these functions can work. All right, we got one more of these to do. Similar situation, but now we have a more complex or a quadratic total revenue equation that we're going to build. And our total cost equation is almost the same thing, quite similar, but we'll have this different total revenue and then a more complex profit function. Okay, so take a moment now, try to make the total revenue, total cost, and profit equations for this scenario. Okay, what is our total revenue equation going to be? Minus 3Q squared. So P times Q, we're just taking this whole thing, multiplying it by Q. There we go. Total revenue, sorry, total cost. Just gonna add those two things together. I'll just write it out here for clarity. 15q squared plus 175q, similar to the last one, except we have a different constant here, 300, not 500. Okay, and then profits will be total revenue minus total costs. Tell me what that will be from the largest exponent first. Okay. Plus 12q squared. Plus or minus? Okay, so minus 22.5q minus 300. Okay, there's total revenue, total cost, and profit for us. And so same process as before, we're going to do our first derivative, solve for q, and all of that. So start there. First derivative is negative 3 over 2q squared plus 24q. 22.5. So we want to solve for this, or solve for q when this whole thing is equal to 0. Oh, sorry, I got a little ahead of myself there. Q squared plus 4q minus 2.5. All right, I'm not going to have a whole lot of space, so I'll just write it temporarily here on the right, and then we'll put our answers back here on the left. So we have this thing, and we want to try to solve for q. 24q minus 22.5. And here as well, it looks like we could do kind of factor out this exponent, sorry, this coefficient in the front here. So negative 3 over 2 q squared plus, okay, 16 q negative, okay, good, and plus 15, 22.5 divided by 3, 7.5, and multiply that by 2, and we get to 15. Or multiply by 2, we get 45, divide by 3, 15. Okay, so these two terms here, the 16 and 15, they're only one number away. Very easy to be lazy with our sum product method. What are the two numbers? Okay, so q minus 1 and q minus 15 are the two factors that we can take out, and then based on this, we get q equals 1 and q equals 15. So there are the zeros for this function. Q equals 1, q equals 15. All right, I'm going to keep it for now, and I'll have to erase that in a moment. All right, next step. All right, second derivative test. Let's just make sure that these things, probably the same as the last question, but let's make sure the minimum is the thing we think is a minimum is actually a minimum. I think I did this in pink. Doesn't matter. Second derivative will be negative 3q plus 4. And we'll substitute in these values. So this whole thing, again, just save some space here. When Q is equal to 1, our second derivative is positive or negative? That's positive. So we can see this is going to be positive 21. Easy to calculate there. And when Q is equal to 15, this whole thing will be negative. So -3 times 15, -45. So it's going to be -21. Okay, so we have a minimum point here when Q is equal to 1, and we have a maximum point here where Q is equal to 15. So again, technically that's the solution. That's what the question was asking us to find, those 2 points. But let's just do a little more work and see if we can find the actual value here. So once again, trying to tell me what the actual maximum profit will be for this scenario. I need to erase some stuff here to make space. If you want this, take a photo or a screenshot. $375. Do other people agree with the number? Yep. Okay. I got the same thing in my notes. So here, this will be our maximum profit, minimum profit, also going to be just like negative infinity, to get infinitely low. So this is the function, this is the combination that we have of these three. Again, color coded, blue for total revenue, red for total cost, and purple for profit here. So just little things that we can notice. So here's our maximum happening, where Q is equal to 15. We can notice the vertical height here of this green bar, and that's exactly the same as the vertical height between the blue one and the red one at that point for all of these. Because the purple one is just the blue one minus the red one. So all of these heights are matching up here. And also see on the other side, if the red one is larger, then we have that same vertical height, except it's now negative here. So lots going on with these, lots of different equations that we have to make, and then originals and first derivatives and second derivatives, and then substituting back into this one or that one to get this information or that information. That can all get a little confusing. So doing some practice with this stuff helps, or just kind of make yourself a little cheat sheet or something that just helps you remember. But the basic ideas are still the same. First derivative for turning points, second derivative for inflection points. Questions? Okay. Nope. All right. So I did have some stuff with derivative rules. If we had a bit more time, Yeah. If we were doing more kind of theoretical calculus stuff, these would be the next three things. Product rule, quotient rule, chain rule. I don't want to start this now because we don't really have enough time. I think I will do this in the second half of the workshop this week. The first half will be just more practice with this stuff. And then the second half can be this if you're curious. It won't be like formal part of the exam or anything. We haven't had enough time to talk about this. But if you are curious, we can just do some simple examples of this in that workshop. Okay, so again, we're still coming back to these basic ideas of just finding maximums and minimums for a function and just more, we did various applications of them, but the basic ideas are the same. Inflection points, we can find a marginal revenue equation, use that to find the maximum total revenue, and break-even points. We didn't do that today, but we did that in the last class. Break-even points for these more curved functions as well, where we might have multiple break-even points, and maximum profits for all kinds of things. So linear, that was way back before the midterm, and then now quadratic and cubic. So more complex types. Right. Yeah. So in our next class on Thursday, it's going to be just concepts and formulas and methods and the strategies for solving these questions, not actual practice questions. Later today, sometime today, I'm going to put up the slides that we will use on Thursday, except with the answers taken out. And you guys can look at that and see if you actually remember all of those parts. Try to do that without looking at your notes. See how much you just remember on your own. And we'll go over all that stuff on Thursday. And then actual review questions we will do on Tuesday and Thursday next week. Like usual, I don't know why, but your class always finishes early. Anyone have questions before we wrap up? All right, then we're done. See you all on Tuesday, or maybe, sorry, Thursday. I'm getting all mixed up. See you all on Thursday. Goodbye.